mass of 5 kilogram is suspended by two strings, 24 centimeters long, 32 centimeters long, and they're exactly 40 centimeters apart. Okay, so let's see here. Just a rough picture now. I don't know if this is an accurate picture. So say this is 24. The second one will have to be a little bit longer. This is 30, 32, 24, and this is 40. Okay. So determine the tension on each string. So the force, downward force due to gravity is still 9.8 gravity times by the weight. Okay, which is 49 newtons. Now, for this to be just in a state of equilibrium and just falling downwards, the left component due to this string here and the right force component due to this tension here, they have to equal. Okay, so I'm going to call this vector A and vector B. And we know that the magnitude of vector A will equal to, let's call this tension 1 and tension 2. The magnitude of tension 1, okay, magnitude of tension 1 times by cosine of this angle here. Okay, so let's call this theta 1. And the magnitude of B is tension 2's magnitude cosine of, let's call this one here theta 2. Okay, so we need to find what theta 1 and theta 2 is, and we can do that because this is also theta 1 and this here is theta 2, and we can do that because in this triangle all three sides are given. So you can use the cosine law to find this any angle inside. So theta 1 by the cosine law is going to be cosine inverse two adjacent sides squared minus the opposite side squared 2 times by 40 and 24. There are two adjacent sides. Okay, let me punch that in the calculator. 53.13. For theta 2, okay, similarly the two adjacent sides this time is 40 and 32, and opposite is 24. 32, again cosine, the inverse of cosine. Okay, so that's what I get for theta 2. Actually, I don't think I even need to find the angles here, right? We just need the cosine of theta 1. So for example, cosine of theta 1 will be the ratio of this. Okay, so this is actually T1. This was 0.6. Was 0.8. So this is actually T2's tension, 0.8. Okay, and they have to equal to each other. So we can say T1 times by 0.6 is equal to T2 times by 0.8. In other words, T1's tension is going to be T2 0.8 divided by 0.6. Let's divide the top and bottom here by 0.2, and we get 4 over 3. So 4 over 3 is a constant. Okay, the other condition is that if you add up the vertical component of this tension 1 and tension 2, okay, so let's call that T1y for the vertical component, and T2y also the vertical component of this vector here. If you add that up, it should equal to the 49. So that's why it will be in the state of equilibrium. So this one right here will be T1's just sine of the same angle, theta 1, which was 53.13, and this will be T2's sine of this angle here. That's equal to 49. And now I can take this and substitute it in here. So you get T2 times by 4 over 3 times by sine of 53.13. It looks messy, but now we can factor out the T2 and be left with a constant only. So T2's magnitude is going to be 4 times by sine of 53.13 over 3 plus sine of 36.87. Okay, so finally, just to get the tension 2, its magnitude is 49 divided by all of this. Alright, so it's time to punch it all in the calculator. Okay, and we get a 29.4 newtons. So for T1 magnitude, we can go back to here, just get this and times it by 4 over 3. So it's just 4 over 3 times by 29.4. 39.2 newtons. Okay, so we have the magnitude. Of course, we have the angles now. So we have full information about the tension of the both strings.